It's really nice to be here again at my second Euruko ever, talking about Postgres table partitioning. I'm Karen Jex. I'm a Senior Solutions Architect at Crunchy Data. You may or may not know that Crunchy Data is now part of Snowflake, so this is the first outing for my Snowflake t-shirt, but that's a story for another day. So as was already mentioned, I always feel like a bit of an interloper at developer conferences because I'm not a developer, I'm sorry, but I do always like to put up a diagram of my career so far just so I can prove to you that at least I do know about databases. So I come from a DBA background. I was a DBA for about 20 years before I became a Postgres consultant and now Senior Solutions Architect. I'm part of the Postgres community. So if you want to talk to me about that, please do. And I like to talk at database conferences and at developer conferences like this one so that I can share the love for Postgres and databases in general. Okay, so what am I talking about today? And more importantly, probably, why should you care about it? Maybe you're thinking about table partitioning. Maybe you've got a huge database or huge database tables and you want to know how you might be able to use table partitioning to maybe make things faster, easier to manage, etc. Maybe you want to know what partitioning even is, what it's all about. Maybe you want to know what the best practices are. And so I've worked with lots of customers who've been through this thought process, who've asked me lots of questions, and this presentations based on a lot of the questions that they've asked, the things that they've learned along the way. But instead of just presenting a series of questions and answers, especially since I'm well aware that I'm standing between you and your lunch, I thought I would rather tell you a story. So let me introduce you to the fictional heroine of the story, Sophia, a talented and passionate Ruby developer. Sophia's working on the equally fictional NavTracker logistics application that's used by shipping companies to track the movement and status of their cargo ships. Sophia and her small team have built this NavTracker application from the ground up, and it's been an overnight sensation in the shipping industry, and they've now got several fleets of ships using their services. The shipment logs table forms the backbone of their application. It keeps track of each ship's current and historical coordinates, the status, and other important information. The code snippet here shows an extract of some of the columns from that table. It's constantly and frequently updated for every ship, so that might be every few minutes when a ship's anchored, it might be every few seconds whilst it's underway, and also based on events such as loading, unloading, docking, etc. NavTracker is a victim of its own success. So with more and more fleets using the application, some of whom have got hundreds of ships, there's more and more data, there are bigger and bigger database tables and longer maintenance processes. The shipment logs table in particular, as you can imagine, is growing at an incredible rate. It's got millions of new rows being created by this constant status update for the thousands of ships that they've got. Clients start to complain about slow dashboards and delayed reports. Sophia's team notices that the vacuum process takes many times longer than it used to. It takes far too long to rebuild indexes, and purging old data is taking hours. The team's spending more and more time firefighting rather than building new features. Sophia needed to find a better way. So she asked around, she watched some database talks, and she learned about Postgres table partitioning. She found out that she could split this huge shipment logs table into smaller, more manageable pieces. So just so that you can visualize the contents of Sophia's shipment logs table, this is an extract showing just a few rows of each for 3 different ships. She wondered about partitioning the table by ship ID. In other words, using ship ID as her partition key. She could create one partition per ship and each partition would contain just the rows for one specific ship. Any of our queries that select from the main shipment logs table would still see all of the rows, all of the data in that table. But the main parent shipment logs table wouldn't physically contain any data. The actual data would now be contained inside the individual partitions. That type of partitioning is called list partitioning. Each partition contains rows with one or more specific values of your partition key. And it's really useful if you've got a database that's easily separated by a common field across your entire data set. So in Sophia's case, that's ship ID, but you might have data that's separated by region, by warehouse, by fleet, or by any number of different values. To create her list partitioned shipping logs table, Sophia would have to use 2 steps. First, she'd create the main table, specifying list as the type of partitioning and ship ID as the partition key. Then she'd create the individual partitions. She'd say which value or values of the partition key, i.e. which ship IDs in this case, should go into each partition. Sophia realized, though, that actually most user activity happens just on the most recent log entries. For example, the first query here looks at the last 10 updates for ship number 3, or the second query that looks at all ships that were loaded in the past 24 hours. What if, instead of searching the whole of the shipment logs table for that information, Postgres could just look in a smaller table containing just the last day's worth of data? She found a blog post on the Crunchy Data website that talked about the potential performance benefits of table partitioning, and I was paying attention. I know that Matt says everyone loves performance. If you've got a huge table that contains data for example, an entire year, but your query is only looking at a small range of dates within that, Postgres might have to scan that whole table to find just the information it needs. If you partition the table on a date field, so split it into multiple smaller table partitions, each of which covers just a small date range, Postgres can then just scan the partitions it needs rather than going through the entire data set. And it does that using a technique called partition pruning. Partitioning a table in that way, so into ranges of values on the partition key, is called, no surprises, range partitioning. It's probably actually the most common type of partitioning, and it's typically used with time or integer series data. Again, the first step to create a range partition table would be to create the parent table, say what kind of partitioning, range in this case, and the partition key, and in Sophia's case here, that's log timestamp. Then create the individual partitions for your required ranges. So this is just a couple of Sophia's one-day partitions for the 1st of September 2025 and the 2nd of September 2025. It's important to note that the date ranges mustn't overlap. If the date ranges overlap, then Postgres wouldn't know which of the partitions a particular row should go in. And also that the range bounds are inclusive at the lower end and exclusive at the upper end. So the 1st of September partition there does include values for the 1st of September, but doesn't include values for the 2nd. As well as list and range partitioning that we've already looked at, Sophia learned that Postgres also allows hash partitioning and composite partitioning. Composite partitioning is a combination of different types of partitioning. Hash partitioning could be useful if Sophia needed to partition a table where the data doesn't have a clearly defined pattern. The data goes into buckets. The partitions are effectively buckets of rows. So when you create your hash partitions, you use modulus to say how many partitions you want, and remainder to say which values should go into each partition. Postgres allows you to subpartition a table, so you can partition your partitions. And subpartitioning lets you combine different types of partitioning. One of Sophia's team members reminds her that they often need to manage data for each fleet of ships separately, and that they actually have a fleet ID in most of their tables. So they could potentially use list partitioning to partition by fleet, and then use range partitioning to subpartition by log timestamp to get a daily partition for each fleet.
Okay, great.
So Sophia already knows that she needs to decide what type of partitioning she's going to use and which column or columns she's going to use as the partition key, but there are other decisions that she needs to make as well. For example, which tables should she partition? She won't necessarily partition all of the tables in the NavTracker application. The fleets table and reference tables like ship types and status categories are probably much too small to need partitioning, for example. Another decision is, does she or does she not create a default partition? It's kind of the junk drawer of the partition world. So anything, any row that doesn't neatly fit into one of the partitions that you've already defined will go into the default partition. Sophia wonders whether or not it's good practice to create a default partition. Fortunately, she found some useful information in another blog post. She read that on the positive side, if you have a default partition, you won't get errors when you load or insert data that doesn't belong to an existing named partition. So that means she wouldn't need to decide in advance which partitions she needed, and she wouldn't need to make application changes to deal with any incorrect or unexpected data. Although, of course, any incorrect data that does end up in that default partition would need to be cleaned up later in any case. The main issue, though, is that if there's a lot of data in the default partition, it can cause it to take a very, very long time to add new partitions to the table. And that's because Postgres has to check every single row in the default partition to make sure that it shouldn't actually go in the new partition that's being added. And whilst it's doing that check, it takes an exclusive lock on the entire partitioned table. She wonders if she'll need to make application changes. She's heard that applications should be carefully designed to make the best use of partitioning. Will there be schema changes, for example? At the very least, she's going to need to add the partition key to all of the tables that are going to be partitioned, including child tables that wouldn't necessarily otherwise contain that column. So as we saw already, the shipment logs table might not naturally contain the fleet ID, but if she wants to partition by fleet, she's going to have to add that in. Will she need to make changes to her queries? Well, if she wants to take advantage of partition pruning, then she will need to make sure that all of the queries actually filter specifically on the partition key. Sophia starts to think about partition management. She does a quick calculation and realizes that if she decides to partition the shipping logs table by fleet and to subpartition on the log timestamp to create a daily partition for each day's logs, she's going to end up with over 2,000 partitions just by the end of the first year, just for that one table. And she starts to wonder how the team should manage those partitions, when and how, for example, should the daily partitions be added. She wonders if she should look for a tool that can help automate some of the partition maintenance tasks. So she decides to investigate the PG Partman tool, to see if it would be useful for NavTracker. PG Partman is a Postgres extension that enhances Postgres's native partitioning to make managing partitions easier. So amongst the features that it provides is automation of creating new partitions and dropping old partitions based on a retention policy. It uses a background worker process, so it automatically runs that partition maintenance, so she won't need to set up any additional scheduling there. And finally, after making all of those decisions, the team is ready to start actually partitioning the tables. But Sophia finds that it's not as simple as she'd hoped to partition the existing tables. Unfortunately, she can't just convert a non-partition table to a partition table, or vice versa for that matter. She needs to create a new partition table and migrate the data into it. But as we've seen, the shipment logs table is already huge, so that would be extremely time-consuming. And they can't afford to take it offline for long because it's constantly in use. She really, really wishes that she'd known about partitioning at the beginning of the project, so she could have planned ahead and created partition tables from the start. But she learns that PG Partman does have some features that can help to turn an existing table into a partition table. It provides an offline and an online method. So the offline method is the simpler of the two, and it allows data to be moved in small batches, but the data is unavailable during the migration. The online method is a lot more complicated. There's a lot of renaming of objects, recreating objects, moving things in and out of default partitions, etc. And it's less flexible. And there are also some restrictions, such as you have to drop any foreign keys to the table and recreate them against the new partition table afterwards. But it does let you do the migration with minimal downtime. Sophia uses the detailed instructions in the PG Partman docs to plan a careful migration, moving the data in small batches with the most recent, most frequently used data first. Okay, full steam ahead. We'll go to the end of the story to talk about all of the good things that Sophia encounters as a result of table partitioning. And as Matt said, joy is better than performance. It's not all about better performance of the application, it's about making things easier to manage. She found it much easier to manage the NavTracker data lifecycle. The native partitioning Postgres blog post describes how it's easy to store just the data you need. So before partitioning the shipment logs table, if Sophia needed to archive or purge all of the data for one particular fleet, she'd have to do a delete. A delete would be time-consuming, it would generate a lot of WAL, it would leave the table bloated, so she'd probably have to do a vacuum and maybe some index rebuilds afterwards. With the table partitioned by fleet, on the other hand, she could just drop the fleet one partition, which is a much, much faster and cleaner operation. If she didn't want to get rid of that data just yet, instead of dropping the partition, she could use detached partition, and that would mean that the partition becomes a separate table in its own right. So then she could do some archiving, other processing if she wanted to before finally deleting it. Similarly, instead of doing a bulk insert into a table, so say she needs to load data for an entirely new fleet into the table, she can create a new table called Fleet 4. She can use the like shipment log syntax, so she doesn't have to retype column names and figure out exactly what that table looks like. She loads the data into that new table, performs any checks, and then just attaches the table as a partition of the shipment logs table. Maintenance processes became much easier to manage. Instead of one interminable vacuum on the whole table, there are now multiple smaller vacuums, one per partition. And instead of 1 hours-long index rebuild, the index for each partition is built separately. And of course, you can run those in parallel if you've got the resources and you want them to go faster. Another advantage of partitioning that Sophia is keeping in mind for future projects is to help in a multi-tenant environment where your database hosts multiple customers or applications. So each fleet, for example, might be a separate tenant, and fleet operators might be allowed to access just their own data. You could then use row-level security policies to restrict the fleet operators to querying and modifying just their own data. Okay. Despite the success, Sophia did encounter some obstacles along the way. There are some limitations that apply to partition tables and some things that you need to watch out for. We already saw that partitioning existing tables is complex and time-consuming. Postgres table partitioning is improving with every version that comes out, but there are a few limitations. So you can't yet create a global index on a partition table. An index on a partition table is actually a series of local indexes, one per partition. And that means that the primary key constraint on a partition table has to contain all of the partition key columns. And you can't yet merge or split partitions. Partitioning isn't a magic bullet for performance. So you need to make sure that you're actually making things better. The application needs to be aware of the partitions, and queries will need to filter on the partition keys. So Sophia found that she needed to test and needed to make some changes to queries to make sure there were no regressions after partitioning. NavTracker is now faster, more stable, and easier to manage than ever before. The team is no longer held back by their database issues, and Sophia's back to doing what she loves best, which is building and releasing amazing new features. She takes a few minutes to sit down with a coffee and think about what she's learned over the past few months. She's learned that partitioning can be extremely useful to manage huge tables and make them easier to manage. It's much easier to manage the data lifecycle. So for example, purging old data or bulk loading. Maintenance tasks, so vacuums, analyze, index rebuilds, etc., faster. She might in the future use partitions to separate data for different customers or applications to implement multi-tenancy. She was pleased to learn that PG Partman can be useful if you need features that don't yet exist in native Postgres partitioning, and that a carefully thought out partitioning strategy can improve performance of certain queries. She leaves you with a final reminder to think about partitioning right from the design phase of your application if you get the chance. That way, not only do you avoid the stress and the downtime of partitioning existing large tables, but you can also choose your partition keys and the type of partitioning that will work best with your application. So with your application's data access patterns, with your data retention policies, and the way that you need to perform maintenance tasks. And she's very kindly shared links to the documentation that she found useful along the way, and links to some of the blog posts that she read to help get information about the different tools. Thank you very much.